motion of a spacecraft under thrust. The propulsion of a spacecraft depends on the ejection of particles from the rear of the spacecraft at high velocity. These particles gain momentum in the rearward direction. As these particles in the spacecraft form an isolated system, the spacecraft must gain an additional momentum in the forward direction, so that the total momentum of the system, this system here, remains constant. Thus, the spacecraft speeds up. You'll notice also that in the video that I showed the other day, you see the space shuttle ejecting material from behind it, and it's going in the forward direction. Of course, the fact that it uses a swimming pool full of liquid substances every 20 seconds tells you that its weight rapidly decreases. And so in that, you can think about the space shuttle as being very, very heavy, and most of that weight is taken up as fuel. I would say, well, that's debatable, but a lot of that weight would be taken up as fuel. As it burns that fuel, its mass gets smaller, therefore it accelerates even more. Okay. You might have noticed also that the G rate on the G meter on the amount of G's that the astronauts were experiencing inside the space shuttle remained relatively constant. I think it went up to about 2.5 or something like that. It backed off to 1. What they're trying to do there is maintain an acceleration, but not too large an acceleration, such that the astronauts can't do anything. If you get up around 4 or 5 Gs, the astronauts would be gritting their teeth the whole 5 minutes that it takes to get into orbit, which wouldn't be very comfortable. So they don't do that, of course. Consider a rocket moving with constant velocity in space. The rocket and the fuel inside it has a certain momentum. When the rocket engines are fired, the fuel ignites and it expands. This expanding vaporized fuel, consisting of a vast number of discrete molecules, is forced at high speed out of the nozzles at the rear of the rocket. Thus, this fuel gains momentum towards the rear of the rocket, but the rocket and the fuel comprise an isolated system. There are no external forces acting on this system. Therefore, by the law of conservation of momentum, the total momentum of this system must remain constant. Thus, the rocket must acquire an additional forward momentum to cancel the rearward momentum gained by the fuel. Thus, the forward speed of the rocket increases, i.e. it accelerates. So I think we all understand that. Thrusters, we looked at a video the other day on the space shuttle using thrusters to be able to change its attitude very slightly when it is in orbit already. Many rocket engines are very small. For example, attitude thrusters on satellites don't need to produce much thrust. One common engine design found on satellites uses no fuel at all. Pressurized nitrogen thrusters simply blow nitrogen gas from a tank through a nozzle. Thrusters like these kept Skylab in orbit and are also used on the shuttle's manned maneuvering system. New engine designs are trying to find ways to accelerate ions or atomic particles to extremely high speeds to create thrust more efficiently. Ion thrusters use electric fields to accelerate ionized atoms to high velocities and then expel them through the rear of the spacecraft. The IPS provided by NASA's N-Star engine uses hollow cathode to produce blah, blah, blah. You guys probably won't understand much of that, so we'll watch a video. Let me just pause. An alternative method of propelling spacecraft is to use a solar sail, which consists of a very thin fabric which is deployed from the spacecraft in a fashion similar to an ordinary sail on a yacht. As the photons of sunlight strike the sail and bounce off, they gently push the sail along by transferring momentum to the sail. Because there are so many photons from the sunlight, and because they are constantly hitting the sail, there is a constant pressure or force per unit time exerted on the sail that produces constant acceleration of the spacecraft. Although the force on a solar sail spacecraft is less than a chemical rocket, the solar sail spacecraft constantly accelerates over time and achieves greater velocity and doesn't need fuel, essentially. So I might have a, let me see if I can find it. There was a video that I have used that I had shown in a, I'll see if I can find it. Quite large. The mass of the spacecraft and the solar sail is 50 kilograms. Okay, so that's very light. Lighter. This thing has 600 meters squared, but it's lighter than you or I. Photons of light are incident on the sail at right angles to the surface of the sail. The average momentum of the photons is 1.12 by 10 to the minus 27 sec-newtons. And 4.15 by 10 to the 22 photons per second are incident on each square meter of the sail. Find the acceleration of the spacecraft if the photons are absorbed by the sail. And look at number 2, the acceleration of the spacecraft if the photons are reflected by the sail. Why do they have sails that are reflective? Louder, louder, louder. Yeah, that's right. Yeah, double the momentum is transferred to the spacecraft if they reflect as opposed to being absorbed. Yes, that's right. Have a go at this, please. This is not an easy question. Total change in momentum of the system equals the momentum of each photon by 10 to the minus 27. Oops. Actually, I'll get rid of that because I'm not gonna fit it in. It'll look messy. Equals 1.12 by 10 to the minus 27 times 4.15 by 10 to the power of 22 photons per meter times 600 meters squared. Yeah, that's right. The book, your example in your book says 2.79 by 10 to the minus 2 sec-newtons. Somebody confirm that for me, please. Sometimes, thank you. So that's change in momentum, isn't it? How do we get the acceleration? Force on the sail first. Actually, I'll just remove that. Sorry, F equals change in momentum over change in time. Because remember, what each of these photons is doing is when it's absorbed, it's stopping. It has 1.12 by 10 to the minus 27 sec-newtons, and it's going down to 0. So the change in momentum for each of those photons is that much. Change in momentum over change in time. Total change in momentum is 2.79 by 10 to the minus 2. Divided by 1 second, isn't it? Divided by 1. So the force is equal to 2.79 by 10 to the minus 2 newtons. How do I get acceleration? Yes. The acceleration, F equals ma, A equals F on m. Was it 50 kilos? 50 kilos is in SI units. 5.6 by 10 to the minus 4. Meters per second squared. It's an acceleration. What about if the photons reflect? Yeah. Show me that mathematically. Change of momentum is double. It goes down to 0 and then back up to 1.12 by 10 to the minus 27 sec newtons, doesn't it? So delta P, change in momentum is equal to 1.12 by 10 to the minus 27 sec newtons times 2. Okay, so think about it. For those that I hope, I know this is for some people this is a difficult concept. Each photon, it strikes the solar sail. It has 1.12 by 10 to the minus 27 sec newtons momentum. It goes down to 0, and then it reflects with no loss of energy, and it comes back up to 1.12 by 10 to the minus 27 sec newtons. It has 2.24 by 10 to the minus 27 sec newtons change in momentum. If the change in momentum is doubled, what happens to the acceleration? Well, change in momentum is proportional to the force, which is proportional to the acceleration, isn't it? So acceleration doubles. Uh, 1.12 by 10 to the minus 3 meters per second squared. Somebody confirm that for me. Thank you. You don't have a problem on solar sails in your tests. Don't worry about that. Any questions about this concept before I move on to